So we started out by trying to organize our code. So the green apostrophes followed with words and then 3 more apostrophes. Those are the title for what's going to be underneath it is all going to go underneath that. So in this case, this is making a sphere, and then we created our red spheres, or our green sphere and then a red sphere. This red comment, or red wording is a comment. So starting from the beginning, at least with our code, we started with the part 1 of our program requirements. So we had to put in the print and the print to ask. So they're going to ask you the mass, and then here they're going to put the input. So then you would plug in your input. So we went through and added the mass, the initial speed, launch angle, radius, and fluid viscosity. After that, we moved on to part 2, and it was making our spheres and our trajectory. So it tells us to use the make underscore trail equal true, and so we had to Google, of course. So we created the green sphere, and we created the red sphere here.
Which our green sphere does not have any air drag in it at all, but our red sphere does.
Yes, and that will come in later in the code. And then we went down, we knew we were going to have to plot it, and we wanted it to make a trajectile or a projectile.
With a loop?
Huh?
With a loop?
Yes, yeah, with the animation loop.
Yeah.
And so, of course, we had to change our theta into radians. Can't do anything with degrees. And we created the velocities for each one. So they both have the same initial velocity. And then we put max height because we wanted our camera angle when we did the thing to be even.
Our point of origin?
Point of origin.
And then our tangential line would have been to 0 when they were at their max height.
Yes. Yeah. And so we created a while true in order to make a loop, of course. So the while true basically keeps doing something over and over again until you hit break. So we had to figure out, well, we started with our velocities, and we were able to get this formula. So we started out with force equals mass times acceleration, and we derived, as Kira's going to present here, we knew that acceleration was dv dt, and we were able to get from that, we would multiply.
We'll divide the m over, and so we'll have force divided by mass is equal to dv dt, or acceleration. And to get dv by itself, we're going to multiply dt by the force divided by mass. And so we end up with this equation, which is how we get the velocities.
Yeah, it's right here in our thing where we showed it. So we had from force equals mass times acceleration, we were able to get this formula. And then of course when you have gravity, your acceleration is gravity. So we noticed we were going to have to put in constants. We have to put somewhere define that gravity is 9.8, and that dt we needed to make a time step. So we went back up here and defined our constants. After that, we were able to decide we needed to fix a rate, and then we moved on to drag. So drag was part 4 of the program requirements, and it was the formula, the Stokes law. So we wrote that here. We had to move some of the stuff over. So our eta we called viscosity in our code. So we changed that over. Our R is our radius, and our velocity for because our red sphere is the one that has air drag. We ended up putting it right there for our velocity. And then, of course, we were trying to...
We divided it by its mass and then multiplied it by dt.
Yes.
Which is the force.
Yeah, to find the velocity. And then we had to So we came in and did the update positions afterwards. We actually kind of ran this beforehand to see, like what it